Now let us start with some NCERT questions. See, here suppose a pure silicon crystal has this many atoms, right? And it is doped by 1 ppm concentration of pentavalent. Now when I say pentavalent, what kind of charge carrier do you see? Basically more in number. Pentavalent means basically n type. Okay, so which means that we will get Ne. Fine, Ne means electron density, number density. And they have asked calculate the number of electron and holes. Given that Ni, okay, so charge carrier of intrinsic, that is Ni is this much. So here, since they have doped with 1 ppm, ppm means parts per million. So here I have doped with 1 ppm concentration of pentavalent. So Ne will be 1 out of million, 10 to the power 6 of total number of atoms. Right? So this will be Ne. So Ne is 1 ppm of this many atoms. So 1 by 10 to the power 6 into this, you are going to get Ne. Now since we know that one relation of recombination, that's Ni intrinsic ion concentration, Ni square equals to Ne into NH. Okay, so what is Ni square? Ne into NH. So Ni they have given to us, right? Ne I have from the here, correct? So I can easily calculate NH. Right. Now, similar to this, they have asked in board examination in 2023. Just check this out. This is a little simple as compared to the NCERT question. At a certain temperature in an intrinsic, fine, electron and hole concentration is this. Intrinsic means intrinsic concentration for electron holes is this. This is your Ni. For intrinsic, this is your Ni. When it is doped with trivalent, means it will give NH, right? The whole concentration increases to this. So this is your whole concentration. So they have given NH, they have given Ni, and now they are asking the concentration of electron, Ne. What's the relation? Ni, they have given NH, they have given Ne. Relation is Ni square equals to NH into Ne. So what is your Ne? Ni square by NH. Put the value, you're going to get the answer. Yes, okay, so this is the answer. Now, let us see one more question here. VI characteristics they have given. So this is your current and this is your voltage. And they have asked to find resistance of the diode. Resistance means change in voltage by change in current. Okay, yes or no? So here they said at ID equals to 15 milliampere. For 15 milliampere, what is the resistance? Now see here, since there is a change of current, so when they say 15, I will try to see the change in the current in the nearby region. So nearby, I can take 20 and 10. So for corresponding to 20, what is the voltage here? 0.8. Corresponding to 10, what is the voltage here? 0.7. So we write like this. Voltage is 0.8 minus 0.7 and current is 20 minus 10. Okay, so calculate, you will get the value. Since it is milliampere, so here I can write 10 to minus 3. So I get the answer 10 ohm. Now for the next case, VD voltage is minus 10, reverse bias. Okay, so what is the resistance? For this voltage, you can see it is just one current. There is no change. It's almost flat, saturation. So we can straight write the answer. What? Voltage by this current as the resistance. Voltage is how much? 10 volt. What is the current? 1 microampere, reverse bias. Micro means 10 minus 6. So what is the answer? 10 to the power 7. Right? Okay. Now let us go with another question. This is again from the NCERT. In N-type silicon, which of the following statement is true? In N-type means what is the majority? Electrons. What is the minority? Holes. N-type is obtained by doping pentavalent. Right? Yes or no? So let us see. Electrons are majority. Yes. Trivalent atoms are dopant. No. not trivalent. It is basically pentavalent. Correct? Electrons are minority. No. Holes are minority. Yes. Pentavalent atom? Yes. So option C is the answer. Right? So here they have given a forbidden energy gap energy for different material, carbon, silicon, germanium, and they have given us as the options. For this you have to basically know the energy Eg to get the answer. So you have to remember Eg for silicon is 1.1, Eg for germanium is 0.72, Eg for carbon is 5.4 electron volt. Correct? So here see option C is correct. Why? Eg is greatest, then silicon, then germanium. Right? Now next NCERT question. Can we take one slab of p-type semiconductor and physically join to another n-type? Answer is no. When you physically join, fine, it might look smooth, but in atomic scale, okay, they may not be smooth. So see the explanation. However, flat will have a roughness much larger than the interatomic crystal spacing. So hence, continuous contact at atomic level will not be possible. So they may not be continuous, or they will not be continuous. Fine, in the atomic scale. So however smooth you see, but in atomic scale, what happens is that they may not be continuous. So hence we cannot physically join N and P and get what? PN junction diode. We have to take a what? Silicon wafer like this in molten state, and then one side you do with N-type, other P-type. This way we do it. Right? But we cannot physically join N and P separately. Now next, let's see. In unbiased PN junction, unbiased means I have not connected any battery. Holes diffuse from obviously P to N region. Because why they diffuse? Because free electrons in the N region attracts them? No. Okay. They move across junction from by the potential difference? No. They move because of difference in concentration, right? Hole concentration in P region is more as compared to, yes. Hole concentration is more in case of P region, and they go to what? N region. Am I clear?
Yes.
So option is C. So C looks favorite for NCERT here. When a forward bias is applied to a PN junction, it what? Raises the potential barrier? No. Reduces the majority? No. Lowers the potential barrier? Yes, it lowers the potential barrier. Option is again C, favorite. Okay, now in half wave rectification, what is the output frequency if input frequency is 50 Hz? I said in half wave, no change in frequency. If it is 50 input, output will also be 50. Am I clear? Same. But in case of full wave, frequency gets double. In half wave, 50 as it is. Okay? Yes? Now see here. Carbon, silicon, germanium have same lattice structure. Why is C, carbon is insulator, while silicon, germanium are intrinsic semiconductor? Here, explanation. The 4 bonding electrons of carbon, germanium, silicon lie respectively in the second and third and fourth orbit. Okay? Orbit, like for carbon. What is the atomic number? 6, 2, 4. Which orbit? Second.
4 by second.
For carbon it is second. Okay. For germanium it is third, and for silicon it is fourth. Silicon is 14, 2, 8, and this is 4. This is third, no?
Third one.
Third. Okay. Let's see. Hence,
Energy.
okay, silicon germanium hence lie in the third, second, and okay, whatever, fourth. Hence, energy required to take least of germanium. Least for
Required to
germanium.
take.
I think this should be fourth, no? I don't know. This should be fourth, and this is third. So what they say is that actually, see, in case of carbon, what happens is that it is 6, okay, it is 2, and it is 4. So it is near the nucleus.
Yes, sir.
So which means that we need to apply more energy to take out the electron.
Yes, sir.
Okay, or to make it to go to conduction band.
Yes, sir.
Because you must have seen in case of carbon, basically Eg is maximum. Because they are more near to the nucleus. Right? So that must be the case. So followed by silicon and highest for carbon. Hence number of free electrons for conduction in hence the number of free electrons for conduction in germanium and silicons are significant but negligible in C, because they cannot have that energy, which means in this case Eg for carbon, we can say Eg for carbon is highest as compared to silicon and germanium, which is 5.4 electron volt for which carbon. Understood?
Yes, sir.
Okay.